Hello, everyone. Welcome back to week 2 of e-learning. I hope things are going well at home with you and your families. I got a lot of great feedback on the last test question I gave you guys. Was asking how things are going. For some of you guys, it's going okay. A lot of you guys are like me. You're kind of, getting bored a little bit. So just hang in there. Hopefully it won't last too long. But our next topic, let's go and get started on that. It's going to be stars and galaxies. And we don't have much instructional days. So school announced last week that we're going to be out on, I think, May 15th. So we have 3 days a week to learn, and that's about 18 instructional days left for the rest of the year. I will be sending out a modified syllabus because we're going to have to cut some materials because of that. So I'll be sending that out this week, so just be on the lookout for that. Make sure when you guys listen to this video, there is going to be a Google form that you'll need to fill out, and it's really simple. It's just going to be a simple yes or no question. Did you watch the video? I'm doing that just in case we get questioned by the state or something. Did we actually do learning for 3 days? This will prove that yes, we did. So it'll be a simple point too. I might have to start entering that in every week instead of at the end, like I said I was. So just fill it out. It's just a simple yes or no question. Easy way to get participation points in the class. All right, well, let's go and get started. So we're going to focus on stars and, just what makes up a star, energy produced by stars. We're looking at special types of stars. That's what we're doing this week. Next week, we will be getting into constellations. So I do still want to cover that simply because it's something that we can go outside and we can immediately see. And constellations have different seasons. So I think it'd be really awesome for us to learn that because we can go outside right now and look at the stars and figure some things out. So first of all, what is a star? So a star is going to be a bright sphere of very hot gas. Energy is being produced, and this happens from thermonuclear reactions. So this basically happens when you have two hydrogen atoms, they fuse together, and they produce helium. And there's other elements involved with that as well, but that's the main reaction, is hydrogen atoms fusing together to form helium. So some examples of stars, we have our sun, obviously, is our star in the solar system. We have Rigel and Polaris, and we're going to learn some other star names when we get to constellations. So we won't focus too much now on specific star names. So types of energy produced by stars. There are 6 main types. First 2 are probably the most obvious ones since we have a direct benefit from that from our sun, and that's going to be heat and light. Heat can also be referred to as an infrared ray. So without heat and light energy, we wouldn't have any other type of energy on Earth. Plants would not be able to grow. We would not have our ocean currents. We would not have wind. So we wouldn't be able to survive without the heat and light energy from the sun. All energy can be traced back to the sun, or at least our main types of energy. We also have ultraviolet rays. So in the summer, you put on sunscreen. You might want to use UV protected sunscreen. So you have UVA, UVB. So there's different types of ultraviolet rays. So that's another type of energy from stars. Stars also produce radio waves. So you might have interferences every once in a while when you're listening to the radio, and this could just be from the sun. X-rays are another type, and then also gamma rays, which are also called cosmic rays. So these can be very harmful to us, and that's why we have our atmosphere to protect us. So again, these are just a visual representation of the waves. So if we look up at the top section here, so we look at, does it penetrate the Earth's atmosphere? Yes or no. We have our radiation type. That's going to be covering the 6 that I covered. So visible light, this is what we can see. Notice as you go down, this covers the visible light spectrum. So that's going to be the rainbow. So whenever it rains, we can see a rainbow. That is from the sun. So this goes into wavelength how big it is. Radio waves are very long wavelengths here. And as we get to the other end of the spectrum, gamma rays, notice that these wavelengths, these frequencies, are much more crammed together. So that means that they can also cause a lot more damage. So further apart here, your radio waves, not very harmful. Gamma rays are closer together, higher frequency, much more harmful. And the frequency is also represented down here in numeric form. And we don't really need to cover the temperature too much at this point in time. We'll cover that later. Okay, for some reason the E is not showing up, but that is energy is produced from fusion reactions. So that was, again, when we have two hydrogen atoms, they fuse together to produce helium and energy. So we also have some stars can also have other elements in them as well. So mostly it's hydrogen and helium. But you can also find carbon. So that C stands for carbon. Na stands for sodium. Ca is calcium. And Fe is going to be iron. So basically, as these atoms fuse together over time, they become heavier and heavier and heavier to produce these other elements listed here. And they're going to be in a gas form just because it's so hot. Stars are moving in space, so I know we think of our sun as being stationary with us moving around it. But in addition to us orbiting around the sun, our sun, which is again is a star, is also moving very rapidly in space. But from our perspective, it appears to be still, or other stars do, but they are all moving in a direction. So on a clear night, we can see on average about 2,000 stars. So when you have a new moon, which is going to be when there's no moon visible, you can see about 2,000 stars. So throughout the year, it's going to be about 6,000 per year because there is seasons for the stars. And there's also some stars that we can see year round. So we'll get into that when we get to constellations. But for us, we're only going to notice the biggest and the brightest ones. We're not really going to see the ones as far away that are more faint with our naked eye. We need a telescope for those. So our universe contains billions, probably more than that, probably trillions upon trillions of stars. But even with all these stars in those galaxies, it's still going to be mostly empty space. So that's something to think about. Okay, let's just go through some of the characteristics of stars. I don't know why that didn't show up either. Let's get that. Okay, for some reason it's not translating well to my Chromebook, or my MacBook, I mean. But anyways, distance of stars are going to be measured in light years. So we talked about that in the last unit. And the method of measuring the distance between stars is going to be called a parallax. So closest star is going to be Proxima Centauri, which is going to be about 4 light years away. So here we have just like a model of our solar system. And again, remember the distance between Earth and the Sun is 93 million miles. The distance between the Sun and Proxima Centauri, which is our closest star, is 4 light years away. So huge difference there. Okay, size of stars. There's 3 basic sizes. We're going to have dwarf stars, and this is what our sun is. It's going to be a yellow dwarf. This can be fairly small, like as small as Earth in some cases. You can have giant stars. So Arcturus is an example there. And then supergiants. So supergiants are going to be about 2,000 times the size of our sun. So Betelgeuse is an example there, and Antares. And I think I saw in the news that Betelgeuse, which will be found in the constellation Orion, I think that's the one that might go supernova here soon. So that is one to look for in the news. Just some diagrams for some perspective here. If you look at this on a scale, the Earth is invisible. Jupiter is the size of 1 pixel, which is going to be one little square of coloration on this photo. Here's our sun. Sirius is a white dwarf. Our sun is a yellow dwarf. Pollux is right here, and then we have Arcturus. This was our giant star that we talked about. So huge difference between a dwarf and a giant. So our next one is going to be a supergiant. So here we have, it's kind of hard to see because this thing's in the way. I don't know if I can move that. Nope. And I just got out of there. Okay, but anyways, Jupiter is going to be invisible at the scale. Our sun is 1 pixel. Here's Sirius at white dwarf. This is Arcturus, which was the giant here. So this was our giant. This is how big it is compared to our supergiants, Betelgeuse and Antares. So these are going to be supergiants. So huge, huge stars here. It's really hard to imagine just how big, but this is a scale for reference. Okay. So another characteristics of stars that we can look at mass and density. So mass is going to be determined by mathematical numbers. So you're going to look at basically the elements in stars, and you can calculate the mass based on the size and the types of elements in there. Most stars are going to be similar to our sun. So our sun is very average. Density, again, is mathematically calculated based on the volume and the mass. You can also look at the elements found in there and the ratio of those elements. So, for example, Betelgeuse, which was that supergiant, is going to be 1/10 of a million of our sun. So the atoms are very far apart. So that last slide that I had with Betelgeuse is actually going to be less dense than our sun. Sirius, which was that white dwarf I showed on the first slide, that is going to be extremely dense. And if you had 1 teaspoon of its atoms, it would weigh 1 ton on Earth. So density can play a big part in the star's life cycle as well. We'll skip that video. It's not really important, and that's not showing up again for some reason. Okay. Now, composition of stars is our next one, and I kind of alluded to that a little bit on the last slide. So with our composition, we can look at spectroscopes, and if you were in my chemistry class this year, in December, if you remember, we used spectroscopes to look at light, and we could determine like different bars of light and what colors they were. If you don't remember that, it's okay. Or if you were not in my chemistry class, it's also okay. But basically, there's technology and tools out there to use light, and we can determine what chemical elements are in objects based on the light coming in. So it's kind of neat that we can do that. Most stars, again, hydrogen and helium, mostly hydrogen. And then next is helium. And then everything else is going to be your heavier elements. Okay. Next is going to be star temperature. The hottest star type is blue. The coolest is red. So again, the hottest flame or star color is blue. Coolest is red. So in chemistry, we use the Bunsen burners. That blue flame means it's the hottest type of flame that we can have. You want that blue flame. So with stars, if it's a blue star, it will be the hottest type. Now the color is determined by the age of the star and the temperature of the star. So if we look at this chart, you have something called spectral type, which is how we classify stars. It goes along with color and temperature, and then also just special features, which is just basically what it's made of. So spectral type, you have O, B, A, F, G, K, M. There's an acronym to remember that, but I'm not going to make you guys memorize that, so we can skip over that for now. But if you notice, the hottest star type, so this is in Kelvin, which is a degree of temperature. It's a type of temperature. But the hottest flame is blue. The cooler stars are red, which that's still pretty hot though. And then we are, I think, in the G with our sun. Okay, star brightness is going to be measured by magnitude. So the lower the magnitude number, the brighter the star or the planet. And apparent magnitude is what we can see on Earth. This depends on the distance it is from the Earth. So usually your closer objects will appear brighter. So for example, and I really wish this wasn't in the way. Okay, so for example, we have Spica is at a 1, Betelgeuse is at a 0.4, and even though it's so big, it's, not that bright. If we go in here, negative numbers, these are our brighter ones. So Sirius is our brightest star that we have all year long, 1.4, or sorry, a negative 1.4. Mars is and Jupiter and Venus. These are visible planets with the naked eye. You can see Venus out in the night sky currently. I encourage you guys to look for that. It should appear on the in the west side of the sky if you look at it in the evening. Okay, so the moon and the sun will be the brightest at negative 13 and negative 27. So the lower the magnitude, the brighter the objects. That's for apparent magnitude. Luminosity is going to be the absolute magnitude. So we're going to look at the real brightness of a star, and this depends on the size and the temperature, not the distance. So if all stars were on equal distance from the sun, from us, some will be brighter than others just because of their size and their temperature. And again, our sun is average, and if we look at this, so we have our, let's get in the way. So basically, what I'm saying is that the size, the temperature, that is going to be your luminosity or absolute magnitude. So that plays a big factor in the real magnitude of it. Okay, star brightness will also depend on temperature. So the hotter the star, the brighter the star. The size of the star, typically the bigger the star, the brighter the star. So hotter, bigger means brighter. And also the distance from the Earth. So we talked about that. Closer to Earth, the brighter it is. Further away, it will appear fainter. So the faintest one that we can see with our naked eyes is a +6 in magnitude, which is very faint. Okay, special types of stars. We have binary stars, which are going to be double stars. So this is when two stars orbit around each other. So it's a common point in gravity. So more than 1/3 of all stars of this type. So basically, you have two stars. That's why it's binary. Bi is 2. They orbit around each other. So this is Albireo and Cygnus of Swan. So it's a binary system. So they orbit around each other. Variable stars, we have 3 types of these. Variable stars basically mean you have a change in brightness, so like a pattern. So like dim, bright, dim. You have Cephala variable, 5-day pattern. We find distant galaxies with these. You have the eclipsing binary. So this is when you have 2 stars orbiting each other, and as it does that, one crosses the path of the other, and it blocks the light while they're orbiting each other. Then you have pulsars or neutron stars, and these give off regular pulses of radio and light waves. So pulsars give off light in a very rapid pattern. Okay, we have not too much more left. Okay, neutron stars are going to be your pulsars, and this is going to be basically your remnants after a supernova, so everything's kind of exploded, and then this is what's left over. So you have your dense areas, and these are your protons and electrons combine, and they form neutrons. That's why it's called a neutron star. So it's so hot and dense that is able to happen. Now, so remember, protons are positive, electrons are negative, if you remember that from chemistry class, and they combine to form a neutral neutron. All right, now eventually they go from a pulsar to a neutron star. So that's part of the life cycle of a star. Next, we have novas. So this is when you have a giant star, and it will kind of suddenly increase in brightness, very, very bright. Then it will fade back to its former dimness. This is basically the end of the life of a star. It means it's dying. So nova is going to be new, but actually means it's a dying star. And this is an example of Delphinius, the dolphin. There's a constellation, and you had a nova happen in this one. Okay, a supernova is when you have typically a supergiant star, and it's going to get suddenly very bright and will explode. And these are very big stars. So you're going to have a very brilliant white light in the sky. This does not happen very often, so it occurs in our galaxy from what we can see about once every 100 years. So that's why you guys should check out Betelgeuse, and maybe one day, sometime soon, within our lifetime, we can see a supernova, which would be kind of neat. This is an example of the leftover of a supernova. This is a Crab Nebula found in Taurus, and this is the remains of the supernova that happened in 1054. So these are pretty well documented throughout history. Quasars are going to be faint star-like objects, which are larger than any known star, and the most distant objects that we can see in the universe. So these are 1 billion times brighter than the sun. And because they're so large and bright, that's the only reason why we can see them from that far of a distance. Okay, star clusters. These are going to be loose groupings of stars in space, could have formed from the same nebula, which is the beginning of the life cycle of a star. These are much smaller than constellations. We'll cover that more next week. The Pleiades will be an example. This is called the Seven Sisters in Taurus the Bull, and I'll cover that next week. But you can see this currently in the night sky. You have Orion. You can find Orion by its belt. And then you have, I think this is Betelgeuse, Rigel, Aldebaran's the Eye of the Bull, and then here's the Pleiades. Okay, Hertzsprung-Russell diagram. So we have 2 more things to cover, then we'll be done. So the Hertzsprung-Russell diagram is going to be this chart right here. It's going to be plotting, again, the categories, the temperature on the x-axis. You're going to have the luminosity or the brightness on the y-axis. And this just goes through the life cycle of a star. Your main sequence, which is shown here, so you can see it labeled main sequence, is where most of your stars are located. Here's our sun. So our sun's pretty average. You have your white dwarfs down here, your supergiants, and your giants. So you can see most of these stars fall along this main sequence. Okay, and our last thing to cover is going to be the life cycle of a star. So it starts off as a nebula, which is just again, a cloud of gas, very hot gas, and can have 2 pathways. I'll go through both of those. First one is a main sequence star, which is us, our sun. Eventually, our sun is going to expand to a red giant, and it would expand to cover us, Earth, Mars, the first half of the solar system. Next, you have a planetary nebula, so it expands even more. Then it will kind of shrink, excuse me, to a white dwarf, and then eventually it'll turn to a brown dwarf and then a black dwarf. So it's like the death of a star. The other route it can take can also circle back to a regular nebula, then go through that sequence again, or it can go to a massive star, depending on how big the nebula is. It can expand to a red supergiant. Then this star will eventually explode into a supernova, and it can have 3 pathways from here. It can turn into a neutron star. It can collapse to something so dense as a black hole, and a neutron star, black hole. These are both very, very dense, by the way. Or it can go back to a nebula and start the cycle over again. Okay, I think that covers it, and I hope you guys have a great week. Let me know if you need anything.